just going to start. I'm just going to tell you a little bit about the Oxbridge Network, and also I'm going to tell you about the forthcoming lectures that we're going to have in the summer term. This is the last lecture of this term. There seems to be a bit of interference here, so I don't know where it's coming from, but there does seem to be a bit of interference. If anybody's got their microphone on, it might be a good idea to switch it off for now, please. Okay, brilliant. Right, the Oxbridge Network is running a series of lectures, and they are designed to ensure that you have an opportunity, all you students, to be curious and actually think beyond the envelope, and actually think beyond your subject as well, and make links between things that might not ordinarily have been apparent. So this is an opportunity for you to stretch yourselves, and each lecture is going to be about a different thing in a different discipline. So this should give you quite scope to be thinking across the board. So where I'm going to start is we're going to talk about the lecture 4, of course, is by Mr. Geddes Cureton of Solihull. And this is the title. You can read it for yourself. Mr. Cureton will introduce himself and also talk about the lecture. But I'm just giving you advance warning now of forthcoming things in the Oxbridge Network. So on the 11th of May at 6 o'clock, at altered time at 6 o'clock, we've got Dr. Stuart Hart talking about Virginia Woolf and literary impression. So art students, an absolute must, but science students too, actually, because this could give you links to various other things. On the 8th of June at 5 o'clock, we've got Chris Priestley, who's going to be talking to us about the physics of internal combustion engines. And I am actually booking for September. So when we actually have our next lecture, you will have some September, October and November dates for the Oxbridge lecture series as well. Okay, other things I just want to draw your attention to. If you're in year 12, you really should be applying for the Oxbridge Network Essay Prize. There are 9 prizes and it's cash prizes as well. Solihull is sponsoring it, and it's open to all the network schools. So if you don't know anything about this, please ask your Oxbridge coordinator or your head of Oxbridge or your head of sixth form in your school. And please enter. The deadline is summer half term. And also on the 30th of March, which is the day before we finish, at 5 o'clock in person, there is an Oxbridge tutorial event, which will give you experience of an Oxbridge tutorial or an Oxbridge seminar. And that really should give you a bit of a something to think about. Okay, if you've got any questions, please ask your Oxbridge coordinator or your head of Oxbridge or head of sixth form. And if you can't get any answers there or they don't know, then please contact me via email, and my email address is on the screen. Now, I'm actually going to stop, if I can manage to do this. I'm going to stop presenting and I'm going to pass over to Mr. Cureton, who is going to introduce himself and is also going to deliver our lecture this evening. And we're extremely grateful to Mr. Cureton. I've seen him before and he's actually very entertaining and very intellectual. So I'm sure you're really going to enjoy the lecture that we have for you this evening. So over to you, Mr. Cureton. I am going to pass you over now for you to share your screen.
Okay, hello. Hopefully you can hear me now.
Yes, we can hear you.
Wonderful. Right, I'm going to try and share the screen, and hopefully in a moment you'll be able to see the words. Can you prove it?
Yes, we can see that.
Perfect. Well, I'll make a start, and thank you for that lovely introduction, Dr. Foster. I'm not sure about being intellectual. Hopefully I will make up by being at least somewhat entertaining. So I am Geddes Cureton. I teach maths to lots of different year groups at Solihull School. This talk is going to have some themes of A-level maths, but if you're not an A-level mathematician, that's not a problem at all. If you are an A-level mathematician, you can possibly recognise some of the different topic areas. So I'm going to be talking about being sure and proof today. I'm going to launch straight into it with the idea of what does being sure or proof mean to a mathematician, and we can do this with a little game. So if you've got the screen in front of you, you can put your finger on any smiling emoji. If it's a touch screen, you might want to just point at it instead. So choose a smiling emoji and put your finger on, and we're going to play a stepping stones game where I'm going to give you some instructions to move up, down, left or right. So from where you started, I want you to move any emojis by going up, down, left or right. And I'd like you to have a go at that now. So move 5 places, so not diagonally, and count, and you will end up on a different emoji. And I'm going to try to predict one that you didn't land on. Okay, hopefully you've moved 5 places from your smiling emoji by now. And I have already predicted that you would not end up on that shape. So from where you are now, I would like you to move 3 squares. And I predicted that you would not end up on that emoji. Hopefully you've got the idea now. We can speed up a little. So I'd like you to now move 4 places, again, still keeping on the emojis like they're stepping stones. And now 1 square and 4 squares. 5 squares, we're nearly done. Hopefully I haven't removed the emoji you're standing on yet. 3 squares. And finally, you should have only one option, which is to move on to the sunglasses emoji. And if that all worked, which could be a minor miracle, you should have got onto the sunglasses emoji. If it didn't work for you this time, perhaps have another go on the recording. And I can say I was sure that it would be that, given that we did everything right. And this is what being sure means to a mathematician. Here are the slides, by the way, that I used, hopefully to indicate that I wasn't cheating and doing anything on the fly. It was all predetermined. So we've mentioned already the word sure. What does that mean? Well, the dictionary definition is rather circular. It just says sure means being sure. So all I'm going to say from this point on is sure kind of means what you expect it to mean. I hope you don't think that's a cop-out, but if I said I'm sure of something, you'd have an understanding of that. For now, that will do. So I'm going to set the scene about being sure about things. And imagine that you meet a chap and he offers to play a game with you. And he's got 3 cards to choose from. And you're going to pick a card at random. If you choose the Queen of Hearts, you win £5 and it costs £1 to have a go. Now, if you're a decent mathematician, you would imagine that that's a good idea because it's going to cost you £3 to have 3 goes. But in that 3 goes, you would expect to win at least once, and that will give you a prize of £5. You might not win, but you would expect to win once out of 3. So you decide to have a go, although you're suspicious that he might not be being fair with you. So you pay £5 and the cards you get are lose and lose again, lose again, lose again, and lose again. So you've played the game 5 times and it's come up ace of spades every time. So you've spent £5, not won at all. But you're happy to have another go. So you spend another £5 and you lose another 5 times. So you keep failing to get Queen of Hearts. By this point, you're just, I think, interested to see whether you're being cheated or not. So you want to collect some evidence. So you pay a final £20 and have 20 more goes, and they all come up ace of spades. So do you expect, or are you now sure that this chap is cheating? Well, we can inform the decision with a bit of maths. And the chap at the moment just says, bad luck. We can use our maths to try to figure out what's gone on. So the probability of an ace of spades would be 2 out of 3. So if you're not being cheated, the probability of 5 ace of spades would be 2/3 times 2/3 times 2/3, 5 times over. Every time you're kind of getting 2/3 of the probability. And that works out to be about 0.131, not that unlikely. You would expect to be dealt 5 ace of spades about 1 time in 7 or 8. So that should not make you all that suspicious. It's not that unlikely an event. But if you look at being dealt 10 ace of spades, that's 2/3 to the power of 10. So rather than keep multiplying, we can just do 2/3 to the power of 10 to do the multiplying for us. And that becomes quite a lot less likely. You'd only expect to choose an ace of spades 10 times in a row, about 1 time in 58. So that would make you more suspicious that you're being cheated. But 30 ace of spades in a row becomes a very unlikely event. You would only expect that to happen if this man was playing fair with you 1 time in 192,000-ish, close to that. So, got some options. One is you've just experienced a once per 192,000 event, 30 ace of spades, no queens of hearts at all. Or he was cheating. And the maths way of saying he was cheating is that the probability of getting an ace of spades is more than 2/3. It's not 2/3 as you would expect. Now, things could happen. You could accuse him and he could be a cheat, in which case you're correct. That's a good result. You could accuse him and he was being fair. That is called a type 1 error. And as we've seen, that would be very, very unlikely. Also, you could not accuse him, but he was cheating. Counts as a type 2 error, because you should have accused him because he was cheating. And finally, you don't accuse him and he was playing fair with you. Just occurs to me that. Move that. Okay, so we're going to now go up what I call the sure scale. So talking about how sure you are. And the lowest standard is by law, which is called balance of probabilities. Now, to talk very briefly about that, this balance of probabilities would be used in various civil cases. And in that case, a judge would decide that the more probable should succeed. Now, to give you a little example of this, but an oversimplified, imagine a class of pupils and they're mainly girls, and a teacher says one pupil will be selected at random to choose the film we watch. And the boy quite rightly thinks, I bet it will be a girl because there's more of them. A random choice would be more likely to be a girl. However, the teacher actually ends up selecting a boy. Now, the girls are beginning to think that's unfair. And so they could claim that the teacher is being unfair. And by the lowest standard of balance of probabilities, they could make that case. Although a judge would be very suspicious of that, just because it's mathematically more likely does not give the evidence, certainly, that a judge would be looking for. So we can move up the sure scale, up to science, where we conduct what we call a hypothesis test at 5%. And hopefully a lot of the A-level mathematicians are thinking, we know this, or we're certainly about to know this. If you don't know anything about this, that's fine. We'll take a look. So imagine now that the teacher randomly selects a boy the next 2 times. So that's been 3 boys now, and the girls are beginning to get annoyed. So they figure out that it's time to tell another teacher, and she's very good at maths. She can figure out the probability of choosing a boy 3 times is a quarter of a quarter of a quarter, which turns out to be 1 in 64. So remember back to the card example, a fair teacher could produce 3 boys, one after the other, but that is a 1 in 64 event if the teacher's playing fair. So by the 5% hypothesis test, we would say that something odd is going on if we get any result that's below 5% to happen fairly. And the chance we've just figured out of a fair teacher choosing 3 boys is below 5%. So the teacher at the 5% level would agree with the class that something odd is going on, and the girls say, I knew it. Now, You might not think that's a very good standard, but it's used in a lot of different fields, as listed, especially medical trials. If an event is less likely than 5% to happen by chance alone, they call that a statistically significant result, and that is evidence for what they're claiming. Let's move up. Reasonable doubt in law. Now, I have no training in legal things, so I just Googled the definition, and it's basically to do with there being no reasonable doubt in the mind of a reasonable person that a defendant would be guilty. Now, a good example of this is an old case involving DNA evidence. And when this case was formed, the chance of two unrelated people matching with DNA was about 1 in 37 million. And so this is so unlikely that a poor chap called Raymond Easton was arrested because he was a DNA match for a crime committed 200 miles away, because the court took the opinion that it's so unlikely to two people to match. But he wasn't guilty. Excuse me, clearly not. He was 200 miles away. He was actually very unwell at the time, and lots of witnesses to say he was there. Now, that mistake is less likely to be made these days, because now, again, the A-level biologists' ears will prick up at this moment. We now compare alleles at 13 locations, and that's much less likely to be a mistake now. Moving on from law is science, which would define itself as having a 5 sigma scale. And the numbers involved in the sigma measurement go up quite dramatically. So by 5 sigma, we're talking about an event that would happen in about 1 in 1,700,000 time. For example, you might have read in the news over the past few years that evidence has been found for a Higgs boson particle. Now, for science to claim evidence of a particle, that's about 3 sigma. But for science to publish that they have discovered the particle, they need results that would only have happened by chance alone 1 in 1.7 million times. So it's very unlikely that this was just a fluke result, much more likely that there actually was a Higgs boson particle. And that's good enough for the scientists, and they publish discovery at that point. We could actually apply the 5 sigma standard to the boys and girls situation, and 5 sigma being that unlikely, we could just keep multiplying by quarters. So the chance of one boy being chosen by a fair teacher would be that, 2, 3, 4, 5, 6, 7, 8, 9, 10, and by 11, we've finally gone below the 5 sigma chance. So if the teacher randomly selected a boy 11 times in a row, that would satisfy scientists that the teacher was being unfair. And it's such an unlikely result to have happened by chance alone. And hopefully you would be convinced by that as well. Say to the teacher, what are you doing? Now, finally, the main event. We move on to complete certainty in maths, so proof. Now, to discuss this, we need to discuss the difference between maths and science. And a nice way to think about this, which I use with younger pupils, is to think of the pets that maths and science might have. So science has a pet called theories, and theories are always improving in the light of new evidence. So, for example, a very famous one is the theory of gravity. Now, Newton's theory of gravity, as evidenced by this equation comparing two masses and the distance between them and the gravitational constant, A-level physicists may recognise this, is an excellent model of gravity, but it's not the whole picture. This can be improved on by Albert Einstein, who, please don't ask me about this equation when it comes up. I'm not a physicist, but this is to do with relativity and a better understanding of gravity. But even at this point, that's not the end. Scientists continue to find new improvements to our understanding of gravity. Note, by the way, as well, if you're doing statistics, how much statistics is used in theoretical physics. We're collecting data to find evidence about those things. So theories in science are always improving, but maths have conjectures instead. And conjectures can be proven or disproven, and that settles the argument forever. Now, If a conjecture does get proven, it becomes promoted into being a theorem. And actually, if a conjecture is disproven, we can usually get a theorem out of that as well. Could be not a very good theorem, but it will be a theorem nonetheless. So let's look at some really simple ideas. Oh, before that, I always do this, forget what I put in the slideshow. So, for example, here is an old conjecture set by Fermat in the year 1637. And this remained a conjecture for more than 300 years. So this is where conjectures do not like to be, no man's land between being proven or disproven and getting promoted to becoming a theorem. However, 300 or more years later, the argument was settled by a chap called Andrew Wiles, and it became a theorem. It was still called Fermat's theorem, Fermat's last theorem, in fact, and it's very famous. Should really be changed to Wiles' theorem, perhaps, but this is the way history goes. So here's some really simple conjectures. So I could conjecture that there is an odd square number, and there is. 25 would be an example of that. So that becomes a theorem. There is an odd square number. That's proven. We give an example of one. A similar one, we could say conjecture 1,000,000 is the largest number. Well, we can counter that by saying, no, there is the number 1,000,001. So, but it's still a theorem. Not a brilliant theorem, but our theorem is now 1,000,000 is not the largest number. Still a proven theorem. Now, unfortunately, this gets onto another circular issue, and this is one for the philosophers. What do we mean by proof? And again, if you look for the dictionary definitions, they're pretty circular. Proof is proof. And so we get into truth. What does true mean? Same thing. Circular arguments, fascinating circular arguments. I heard a whole Radio 4 programme once discussing this, and it goes over my head philosophically. But in maths, we have another pet to help, and these are called axioms, and they are just true because they say so. If you've ever spoken to a small child who says why, and then you explain, say, yeah, but why, and then you explain, but why, eventually you say, because I say so. And this is the maths axiom. It does that job for us. So, for example, maths axioms could include two numbers a plus b is the same as b plus a. It can be said to be true just because we say so. It's defined as being true. Axioms, let you read those in your leisure, things that you will recognise, but would be hard to explain at a deeper level. So we can just say it's now an axiom. It's true because we say so. Now, let's have a think about being sure and trying to get a bit more of an interesting theorem than we've had so far. We've only had some very simple ones. So, another mind reading trick. And I've put the answer, Darren Brown, you may recognise from the television, he's holding it at the moment. And we want you to think of a whole number from 1 to 10 inclusive. We'd like you to double it, then add 8, then halve it, and finally subtract the number that you first thought of. And we predict the answer is 4. Hopefully you did get 4. Again, have another go on the recording if not. Now, conjecture 1 is that the trick works for any number you could have chosen. Now, how can we prove conjecture 1? Well, we can prove it by literally trying every number. So if you'd have chosen 1, you'd have doubled it and got 2, added on 8 and got 10, divided by 2 got 5, took away the number you first thought of and got back to 1. This also works for 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10. And that counts as a proof by exhaustion. Exhaustion means using up every option. So conjecture 1 has become theorem 1, and it's been proven by exhaustion. Now, the idea of proving by exhaustion can be really useful in games. So if we can exhaust every single possibility, we can know how to win a game. This is a very simple matchsticks game where you take it in turns with an opponent to choose 1, 2 or 3 matches. And the loser is the person who has to take the Justin Bieber CD. Or you could say the winner if you like Justin Bieber. Okay. So we can map out that there are 927 different ways that game can go. Now, if you want a real challenge, see if you can arrive at that number. It's a problem of combinations. The game theory, by the way, says that split the matches into groups of 4 and let your opponent go first, and whichever they take, you add their score up to 4. So if they take 1, you take 3. If they take 2, you take 2. If they take 3, and you basically win each group of 4 until your opponent has to take the last match, and they're left with the Dustin Beaver CD. Have a go at that. Does it work on more complex games? Yes. So, for example, perfect play in noughts and crosses involves, well, the girl in the picture is looking pleased with herself because she's made perfect play. She's gone into the corner first, and if the boy goes anywhere other than the centre, which he has done, she's guaranteed to win. That counts as a perfect response, and you can then map out every single noughts and crosses game. And it turns out that there are quite a lot of different possibilities, but easy for a computer to figure out. So you could play perfectly. Doesn't necessarily mean you guarantee a win, but you can guarantee at least a draw. And if your opponent does not play perfectly, you're definitely going to win. Now, other games are a bit more difficult. So chess, for example, which we're playing a lot of in the maths department at the moment, in the first go, you've got 8 different moves you could make, because each pawn can go forward 1 place. Actually, there's 16, because each pawn could go forward 2 places. And actually, there's 20, because you could move each of your knights 2 different places. So by the first go, there's 20 moves. Your opponent can also make 20 moves. So that's 400 possibilities after turn 2. And as you read up the table of possibilities, it goes very, very big. And it gets very soon beyond even a powerful computer to map out all possible chess games. So which games have been solved or mapped out by exhaustion? Noughts and crosses, the matchsticks game, English drafts on an 8x8 board, if you play that. It seems a bit bleak, doesn't it? If you're playing that, you're wasting your time because it can't be won. Connect 4, likewise. But other games still not been mapped out. Chess, as we said, my favourite, Othello or Reversely. And also games like Go, which are very popular around the world. Back to Darren Brown's trick. What if we make it conjecture 2 that the trick works for any number? This is much more difficult now. So can we prove this by exhaustion? I'll leave you to think about that for a moment, but there are an infinite number of numbers that this needs to work for. So in maths, what we often go for then, if we couldn't do it by exhaustion, we might try to find counterexample, and just one will do. So let's have a go. Counterexample. So we might try 0, double it, add 8, divide by 2, take away the number we first thought of. What about a negative? Double it, add on 8, divide by 2. Now, when we take away negative 3, we go up to 4. So still not a counterexample. Fractions, double, add 8, divide by 2, take away the 5th. Decimals, we shouldn't expect should be any different. And again, this is exactly where the conjecture does not want to be. It's not proven, it's not disproven. However, we have other techniques. So algebra is excellent in maths for numbers that we don't know. So we could let the first number that the person chose be x, and x can be any number, doesn't have to be whole. We could then multiply by 2, add on 8, divide by 2. So by this time, we've got the number that the person thought of plus 4, and then when we take away the number they thought of, we inevitably end up at 4. So now x that could represent any number now shows that we can eventually always end up on 4. And so we can say conjecture 2 also is now proven using algebra. Interesting to ask, does disproof by counterexample then ever work? Are we wasting our time? Well, let's have a look. There's a fascinating puzzle of dots and areas. So if we draw a circle and we place a dot on the outside, that gives us one big circular area. And the pattern is that we need to add a dot and join them all up and then count the areas that we've now got. So now 2 areas, add another dot, 3 dots, and count up 4 areas. We might be beginning to spot the pattern. 4 dots, join every dot up. We've now got 8 areas. Pattern seems to be holding. If you thought it seems to be doubling each time, you could be on the right lines. a fifth dot. So I think it's now time for a conjecture, which is each time we add a dot, we double the number of areas. And we can test this conjecture by collecting information and looking for a counterexample. So 5, let's count them. I'm colouring them in as I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 areas, rules working. Again, in maths, we learn that just because a pattern seems to be working, we cannot take that as proof. Add another dot. Take a deep breath and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Oh, 31. And hopefully you don't think I cheated you. There really is 31 areas. So each time we add a dot, we double the number of areas. No, actually, we've disproven it. So we get a bit of a rubbish theorem 3, that we don't double the number of areas each time we add a dot. Mind you, even a rubbish theorem can lead to a better theorem. And if you do the maths, and this would be an excellent exercise for you if you're an A-level mathematician, we end up with a quartic formula, which I'm not going to talk about now, which would be theorem 3, that is the number of areas compared to the number of dots n. But go at another example where we might want to find a counterexample. And this is an equation made by Brahmagupta many, many years ago. And this is not a particular equation that he wrote, this is an example of. So if x is positive whole numbers, 1, 2, 3, 4, etc., we're going to make the claim that 61 lots of x squared plus 1 is never a square number. Remember, a square number is any whole number squared, like 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, so on. And here's a theorem. Sorry, not a theorem yet. I'm getting ahead of myself. Here's a conjecture that 61x squared plus 1 never equals a square number. So let's try it. If x is 1, 61x squared plus 1 will be 61 lots of 1 squared plus 1, which is 62. Now we can tell that's not a square number, so but we're on our way. That's one of the infinite numbers we need to check. So when x is 2, 61 lots of 2 squared plus 1 would be 61 times 4 plus 1, which is 245. Harder to check if that's a square number. A good way to check it with a calculator is to take its square root, and if that's a decimal, then we know it wasn't a square number. So the conjecture so far, so good. X is 3. The story, 61 lots of 3 squared is 550. That's not a square number. 4 squared, same when we do involving 5 squared. Also, so far so good, but it's going to take a long time. Maybe it would be a good time to use Excel to help us. So let's knock up a very quick spreadsheet. So let's pop in an X, and this is the numbers that we count. And we need to paste in a formula for 61 lots of x squared plus 1. And when we do, our results are as follows. Now remember, we want to see if they're square numbers, so we need to do the square root of those, which Excel can do. And as you can see, none of these are square numbers because their square roots are all decimals. And as we begin to scroll down the sheet, still no square roots. Scroll down the sheet, still no square roots. And you're welcome to set this up yourself. We can scroll all the way down to the bottom where, did you know Bill Gates' picture is always at the bottom of the spreadsheet? Or maybe that's not true. You could prove or disprove me by trying to find the bottom of a spreadsheet. But all the numbers are actually not square numbers. So in summary, we've tried everything from 1 up to over 1 million, and we haven't found a square yet. However, if we were to continue up to over 226 million, we actually do find that 61 multiplied by that huge number squared plus 1 is a square number. You need a powerful calculator to check this, but it's true. So this conjecture 4 is disproven, and it becomes a theorem that sometimes 61x squared plus 1 is a square number. Not always, but there are examples. And remember, we only need one to make our point. This is a good point to bring in a very famous mathematician, Paul Erdős, who's a Hungarian mathematician, and he famously talked about a book that after we pass away and we get to heaven, there is a book that contains all the proofs of all the conjectures, and they're all written in the simplest way. For example, we can make a proof by contradiction. This is where we take a conjecture and then we compare it to its converse, like its inverse, the opposite statement. Now, why would this be useful? There's a very famous example of this. We can make a conjecture, and this is really important, perhaps the most serious one we've done so far, that there is an infinite number of prime numbers. Prime numbers are numbers with only two factors themselves and one. So we're conjecturing that they go on forever. Now, the way to consider this is to think that numbers have factors, and they always come in pairs, like 15 is 1 times 15, 3 times 5. 24 has got loads of factors. 7, just one. So 7 is a prime number because it only has one pair of factors. 1, by the way, is not prime. Now, if we now consider that there is an infinite number of prime numbers, we could compare this conjecture to its converse, which is there is a finite number of primes. Or there is a biggest prime number, is another way of saying that. So let's see if we can establish conjecture the converse of 5. Now, a way to do this would be to assume that this converse is true. And the prime numbers, we've only discovered 3 of them so far, 2, 3 and 5. Well, there is a very clever way to make up a new number, which is we multiply them all together and we add on 1. Now, this number is not a multiple of 2, it's not a multiple of 3, and it's not a multiple of 5. So we suspect that it is in fact a new prime number. So we've generated a new number that is prime. So 2, 3 and 5 were not the only prime numbers. We could try this with a longer example. We multiply all these together, we get a very big number when we plus 1. And remember, none of these numbers so far are factors of this number. We could try dividing every one of these numbers in and it wouldn't be prime. So, however, this does not mean that the number 30,031 is a prime number. It does actually have other prime numbers within it. However, that's still fine. We're going to get 2 options. We either get a summary of what we did. The resulting number will either be a new prime number itself, or it will contain new prime numbers. Either way, the list of numbers we think are all of the primes is not the complete list. And you can make that argument for any finite list of primes. So the logic then goes, we have disproved the converse of the theorem, which then proves conjecture, which then proves the conjecture. So by a converse proof of contradiction, there is in fact an infinite number of primes. And Erdős would say that is straight out of the book. That is a very simple, quick proof. Not necessarily simple. I had to think about that quite hard, but it's certainly quick. We'll more or less finish with the most famous one, which was called Fermat's last theorem, which actually should have been a conjecture. And this involved, you may have heard of Pythagoras' theorem. So, for example, there are lots of examples of a number squared plus another number squared equaling another number squared. And we have to fill these boxes with positive whole numbers. And if we do that, there's lots of examples of, these are called Pythagorean triples. You could keep finding infinite number of these. However, if you try to make a cube plus a cube equal a cube, and you've got to fill these boxes with whole numbers of 1 or more, Fermat says you'll never manage it. You will never ever do it, and you can choose any 3 whole numbers above 1 you like. But also, you can't do it if the powers are 4 in the equation, or 5, or indeed 6, or any number. So any number above 2, you'll never do it. So how can we prove this? Exhaustion is impossible. Counterexample, none were ever found. And a direct argument is really hard. In fact, it took Andrew Wiles, who we talked about at the start of the talk, many, many, many years to get there. So to finally finish off, you might think, well, there's nothing for me to do. Surely there aren't any important theorems or conjectures, I should say, that haven't been proven yet. Well, there are a few. There is so far Goldbach's conjecture. This is a really simple one that says every even number can be written as the sum of two primes. This has never been discovered to be true or false. We very, very, very strongly suspect that it is true, but we have never proven it one way or the other yet. If you could find a counterexample or a clever argument, you could be the person to prove it and make it Goldbach's theorem. You might get to put your name to it. There are others. I'm looking at the time, I'll mention this very quickly. This is called the Collatz conjecture, or the 3n+1 conjecture, which is if you choose any number and make a pattern by, if it's even, you divide by 2, if it's odd, you multiply by 3 and add 1. The conjecture is that you will always end up at 1. So, for example, if I start at 53, that's odd, so I multiply by 3 and add 1. That's even, so I halve it. Even, so halve it again. Even, odd, multiply by 3 and add 1. Halve it, halve it, halve it, halve it again, and we ended up at 1. Collatz conjecture says you will always end up at 1. And again, you could prove or disprove this one. Again, it's very strongly suspected. Possibly your best bet is the twin primes conjecture, because we're getting reasonably close to this. And this is that the list of primes contains an infinite number of twins. These are prime numbers that are 2 apart, like 3 and 5, 41, 43, 59 and 61. And that would be, again, very difficult to prove. But Andrew Wiles says it could be you to be the one. He was only 7 or 8, I believe, when he found out about Fermat's conjecture. And he said, I'll have a go at solving this. And he did. So again, rushing a bit towards the end, because the time seems to have been tight towards that part of the lecture, I will say at that point, thank you very much for listening. Now, I'm going to try to come out of my presentation and see if there have been any questions. So for this, I need to go back into Teams, and I'm going to perhaps stop sharing my screen, but hopefully you can still hear me. And I'm going to look at the Q&A. So
I can't see any questions at the moment, but I was just going to start the ball rolling with a couple of questions from me. And they might be, forgive my complete ignorance of mathematics. So, Mr. Cureton, can you answer this question? What rubbish theorem ends up with a better result? Have you got an example?
Oh, that's a very good question. Well, I think it would be hard to come up with a better example, really, than the circles and regions one that we did. So it's worth just going back into some details with that, because we got a rubbish theorem, if you remember, that the regions don't just double each time. And that is a theorem. We proved it true, but it's not very good. But it does encourage us to then think, well, what is the rule? We can't ever just follow a pattern in maths and say the pattern has worked. You know, so, for example, when we looked at the equation that continued to work all the way through Excel, we can't say, look, it's worked so far, I'm going to take that as evidence. Remember, we can never collect enough evidence in maths. We have to make another argument. And so when we look at that rubbish theorem, that the pattern doesn't just double each time, we can then look, and unfortunately the maths is a bit tricky to explain then, so we get into a field of A-level maths about combinations and permutations, where we end up with a much better rule, which turns out to be a quartic equation. But I think the example I gave would probably be the best one I could think of. Again, any other members of the department may well be saying I will kick myself at the end of the presentation. But that would be the example I would give, is the one from the presentation.
Great, thank you very much. And you mentioned the Collatz conjecture. That was one of the essay questions that we gave for the Network Prize last year. And we had some very interesting essays, and Mr. Bishop would be able to tell you about that. Come on, guys, has anybody got a question for Mr. Cureton? Because I don't want to hog this. I've got 3 more questions, but I don't want to ask them. So, guys, has anybody got any questions for Mr. Cureton? Do you want to type them in the Q&A, please? There's a Q&A button at the top of your screen. We're not using the chat today, but we are using the Q&A. Has anybody got any more questions? Seem to have mesmerised us, Mr. Cureton.
I know, I do feel like I rushed through a bit, but hopefully, again, with the recording that's been made, people can rewind things and check things out. So, yeah.
Shall I ask you another question?
Please do, yes. And thank you so much for having things prepared. That's really kind of you.
Well, I haven't prepared anything really. It just occurred to me.
Even better.
I thought it was very interesting, Mr. Cureton, that you actually went into other disciplines as well. And you looked at the law and you looked at science and various other things. So this is my question. Are all these other disciplines impure, unsure, or simply wrong compared to the rightness or the surety or the purity of maths?
Right, I was just sorry. I do apologise. I was slightly distracted because I've just seen a question pop up. Would you mind repeating that, Dr. Foster? I'm so sorry.
Yeah, okay. Yes, I've seen the question come up. Brilliant. Thank you, Ishmael. Right, this is my question again. Are all the other disciplines that you talked about, law, science, etc., impure, unsure, or simply wrong compared to the rightness, the purity, and the surety of maths?
Right, yeah, excellent question. Thank you. So there's an interesting cartoon about fields of science arranged by purity. I think physics comes out at the top place, and then way in the distance is a mathematician saying, "Oh, I'm sorry, I didn't see you guys over there." And this is a way to kind of classify different subjects, but I find it a bit pejorative, if I'm honest, to say that other fields are less pure. I would say it's probably a function of utility, that sometimes you cannot use. It would be nice to find a proof of something, but there are things that we just cannot know, which is a fascinating field of maths and science in its own case. And at that point, that's when we have to use the so-called less pure fields to answer a question. If we want a useful answer, so for example, you know, if we're going to talk about what will the climate be in 10 years' time, we could not use pure maths to solve that. We would have to collect information. We'd use a lot of mathematical techniques and a lot of data processing and mathematical modelling, but it wouldn't be a pure answer to the question. So I would say maths is great for when there is a pure answer available, but other disciplines then take over when there is no possibility of that, and we are still interested, or we really need an answer to our question. So hopefully that's a good insight, Dr. Foster.
That's great. Thank you very much.
No, thank you. So I'm going to move on to Ishmael's question. So was it an axiom that new primes could be made from a product of primes? I wouldn't describe it as an axiom. That's a really interesting question. It's really nice that you've looked back over the lecture. It was really, I would just call it an idea, that a way to, if we think we've run out of primes, we just multiply them all up and then add one to them. And remember, that doesn't always guarantee making a new prime. It's either going to be a new prime that we haven't thought of yet, or it's going to contain prime factors that we haven't thought of yet. Either way, this idea for generating a new number disproves the idea that there is a finite number of primes, which then in turn proves that there must be an infinite number of primes. It's genius, really. I wish I could have thought of it. But an axiom, I would not describe it as an axiom, just a brilliant idea. Thank you very much. Great question. Valio's got a question. Thank you. So, yeah, did computers or technology take part? Well, they certainly did. The history, very briefly, and there's a brilliant book by Simon Singh about this, of Fermat's last theorem, was that mathematicians came and went, and each one gave it their best shot at proving or disproving the theorem. And then, as per my lecture on fractals, where we talked about computers kind of becoming reasonably powerful in about the 1950s, 1960s, this was meant to be a new dawn in settling questions like this, because as you'll gather, a computer could try trillions of different combinations of three numbers and powers to see if they could find one that worked. And remember, just one counterexample is needed. If you could find that 143 to the power 17 plus 144 to the power of 17 equals 145 to the power of 17, then you've got the proof. And in fact, the Simpsons cartoon joked about that. They put one that looked like a proof, but was actually just very close when you round off. So yeah, computers did play a big part in that. However, the computers were unable to settle the argument. It was down to Andrew Wiles's amazing work connecting lots of different fields of pure maths that actually got the job done. So yeah, computers are really useful, especially if they find a counterexample, but they're not good enough by themselves. Okay, hopefully that's a good answer for you, Valia. Thank you. Another one for Ishmael. So would I agree that in a game like chess, there's a limited number of possibilities because new variables. So yeah, it would be a big number, but it would be limited. Yeah, so I think that's a really good point. So the number of possible games of chess would not be infinite because, well, it would depend on how you categorise things. So if you go around in loops, for example, I think there's a rule about that. If you go through the same loop 3 times, it's called a stalemate. Again, other members of the department who are way better at chess would correct me on that. But yeah, if you think that there is just a finite number of different combinations of the chess pieces on the board, some possible, some impossible, then there are certainly a finite number of possible chess matches. But it would be a very, very, very big number, far too big for a computer to process. But it would be limited, yes, not infinite. Again, that's not necessarily a theorem I've made for you there, but I think you could put what I've said, my conjectures, into a theorem in thinking about total number of possible positions of pieces on the chessboard. Very interesting question. That's excellent. Thank you, Shmal. I think that takes me. It's a new post that I haven't seen yet. So, no, that looks like the 3 I've had so far. Now, Dr. Foster, did you mention you perhaps had a third question?
Yes, and this shows my complete ignorance.
What
is the difference between a theory and a theorem?
Yeah, sure. So that was the difference we said between science and maths. So in science, there would be a theory like the theory of gravity, the theory of evolution, and new evidence, new experiments would keep refining that theory. And sometimes a theory can get abandoned altogether. For example, there was a theory of phrenology, which was that the bumps on people's heads could give a phrenologist insight into their character. This was just abandoned completely because of there being no evidence for it. So a theory in science is improved upon or abandoned. I think, again, scientists get quite convinced by some theories, like they would say theory of evolution, theory of gravity. They're fairly convinced by what they know so far, but it doesn't mean that it won't be refined in the future, or maybe even abandoned one day. It's not clear. Whereas in maths, if you take a conjecture and prove or disprove it, then that is a theorem. And we hope that a theorem is settled forever. Now, Fermat, unfortunately, was one of the famous people to make this mistake. He thought he had solved his conjecture. That's why he called it a theorem. And it was the last theorem he ever came up with because he died shortly after stating it. He also rather tantalisingly stated that his proof of this conjecture was just slightly too large to fit into his margin, so we'd write it down elsewhere. But we never know what he will have thought. An old colleague of mine, Mr. Worrell in the department, said that he managed to prove it for a cut down version, his so-called little theorem. And I think he thought it would generalise. And so even a great mathematician sometimes makes the mistake of saying This seems good. I think it generalises into other cases. So he thought he got a theorem, but he actually hadn't in the end. It's just a conjecture. Well, actually, it was a theorem, but he didn't know it yet. So yeah, theory in science can be improved upon. Theorem in maths is settled, unless you've actually made a horrible mistake. In fact, even Andrew Wiles published it as a theorem, and he did find a mistake. It took him a year to put it right. The story is absolutely fascinating. I would encourage anybody to look at Simon Singh's book about this. I'm just looking again. Don't see any more student questions. We've still got a few minutes before 6 o'clock. So if any of the participants want to type anything quickly, or if you had any other thoughts, Dr. Foster.
I'm just having a look to see if anybody's actually put anything in the chat as well, because sometimes people do that. There is another question, is there? Have a look.
Chat.
Yes.
Oh, right, is there? So Q&A. Let's have a look. Sorry.
No.
No, just those three again.
No, that's right. Yes. Okay. Well, has anybody got any more questions? If not, we will sign off in a moment. We will have done this in a very efficient hour. With some really interesting questions from everybody. If questions actually come to you later on, then obviously this is what it's meant to do. That is what this lecture is meant to do. Okay, so if you have got some further questions, you may, if you're from another school, want to ask your mathematics teacher, or you may want to ask Mr. Bishop here or Mr. Cureton at Solihull. Please don't ask me, because I'm not a mathematician. I can't see any more here. Mr. Cureton, I'd like to say a huge thank you for a very professional lecture, which has raised some very interesting questions, actually, and is pertinent to something that we did with the upper fifth yesterday. And I can see some of our upper fifth here around patterns. So thank you very much. Unless anybody else has got anything to say, then I'd like you to show your appreciation to Mr. Cureton by raising your hand or giving him a clap, please, on the top of the screen.
Oh, thank you so much, folks. It's really kind of you.
Yeah, I can see some people giving him a clap. I can't see. There we go. Yes, that's great. Thank you very much, Mr. Cureton. Obviously, we need to engage you when we're playing chess or any other game, actually.
No, not me. Anyone else from the maths department. They're all better than I am, I assure you.
Oh, right. Thank you very much.
You're welcome. Thank you.
Thank you. And thanks everybody for attending. And this will obviously go on the YouTube channel for the Oxbridge Network. And you will be asked to make some comments if you want as well. OK, we will be putting some opportunity for you to give us feedback as well. There are 3 other lectures on there at the moment, and we will be adding to that. And we'll be putting some more content on a new web page for the Oxbridge Network as well. So please access those when your coordinators actually give you the details. Okay, thank you very much and have a good evening. Bye.